In this video, we'll do another example. In this example, we will have a 2 by 2 matrix, but only one eigenvalue. Consider the following system. It's clearly rather trivial because the equations don't interact, but we can still approach it using the techniques of this section. First, we find the characteristic polynomial, the determinant of A minus lambda I multiply the diagonal and the anti-diagonal elements, subtract them, and set the result equal to 0. We see that there is only one eigenvalue. Disappointing, because we need two linearly independent solutions. And from the previous example, it seems like we're only going to get one. But we'll forge ahead and see what falls out of this. We'll solve A minus lambda I times V equals 0. And we discover that every non-zero vector is an eigenvector. The zero matrix times any vector is 0. In the previous example, what was the reason we needed to use both eigenvalues? Well, it's because even though both eigenvalues had an infinite number of eigenvectors associated with them, they were constant multiples of each other. That is not the case here. Pick two linearly independent eigenvectors. Say this. And this. Form solutions from them. These solutions are linearly independent, even though the eigenvalues are the same. So we can form a general solution. Let's isolate that as a theorem. Suppose that A is an n by n matrix with linearly independent eigenvectors v1, v2, vn, and corresponding eigenvalues lambda 1, lambda 2, lambda n. Then the solutions v sub I e to the lambda I t are linearly independent, and thus can be used to create a general solution. One of the most important things about this theorem is what it doesn't say. We do not need these lambdas to be distinct. This theorem still works if, for example, this lambda 1 equals lambda 2. In this video, we have considered another example of the eigenvalue solution method. We have seen that for an n by n matrix, we don't need n different eigenvalues, but n linearly independent eigenvectors. We can have fewer than n eigenvalues and still get n linearly independent solutions from them without any hassle. Now, this isn't a guarantee. You can have fewer than n linearly independent eigenvectors, and we'll consider that case in due course.